Okay, let's dive into this. We're going to uncover the hidden chemical dance that makes things either heat up or cool down, sometimes right in the palm of your hand.
I mean, you've probably used one of these, right? It feels like actual magic. You snap a little disc or you shake a pouch and poof, you've got instant heat or cold on demand. Well, it is not magic, it's pure chemistry. And by the time we're done here, you're going to know exactly how it all works.
So, let's pull back the curtain on this so-called magic trick. It really just boils down to understanding two very important words that describe how energy flows.
Okay, on one side, you have exothermic reactions. Think exo, like exit. These reactions push heat out into the world. That's your hand warmer getting toasty. And on the other side, you've got endothermic. Endo kind of sounds like in, right? These reactions pull heat in from their surroundings, which is what makes them feel so cold to the touch. That's your instant cold pack.
So, the big question is, how does a reaction actually decide if it's going to give off heat or soak it up? Well, it all comes down to one simple, absolutely crucial rule about the tiny things that hold our universe together: chemical bonds. This is it. If you remember one thing from this entire explainer, make it this. Let's say it again. Breaking a chemical bond always costs energy. You have to put energy in, and forming a new chemical bond always releases energy. That is the golden rule, period.
Now, I know what a lot of you are thinking right now. It just feels right that if you break something, like snapping a stick, energy gets released. But in the world of chemistry, that intuition is actually backward. And honestly, it's one of the biggest misconceptions people have.
Let's make this super simple with an analogy. Picture two really strong magnets stuck together. To pull them apart, you have to yank them, right? You have to use your own energy. You're putting energy into the system. That's endothermic. Now, what happens if you just let them go near each other? They snap together all by themselves with a click, releasing that energy. That's exothermic. And believe it or not, chemical bonds work pretty much the exact same way.
So you see, every single chemical reaction is basically a two-step dance. Step one, there's an energy investment. You have to put energy in just to break apart the old bonds. But then comes step two, the energy payoff. As new, more stable bonds snap together, energy is released out. And the net result? Well, that just depends on which number was bigger. If the energy payoff was greater than the investment, the whole thing is exothermic. But if the initial investment was bigger, it's endothermic.
Now, let's actually visualize what's happening here. We can map out this whole energy exchange almost like charting a hike up and down a mountain. To do that, scientists use a fancy-sounding term called enthalpy change, or just delta H for short. Don't let the word scare you. Just think of it as the final score in that energy tug-of-war. Is it a negative score, meaning heat was released, or a positive score, meaning heat was absorbed?
And this shows it perfectly. This is an exothermic reaction. The starting chemicals, the reactants, are up high on this energy hill. They have a lot of stored up energy. The reaction happens, and the new products end up at the bottom, in a much more stable, lower energy state. That drop in height, that's all the energy that got released as heat, warming everything up. It's literally an energy trip downhill.
So, as you can probably guess, an endothermic reaction is the exact opposite. Here, the reactants start at the bottom of the energy hill, and to create the products, the reaction has to suck in a ton of energy from its surroundings, from your hand, from the air, just to make that climb to a higher energy state. It's a tough uphill battle that leaves everything around it feeling chilly. Okay, let's do a super quick recap. Exothermic, it releases heat so things get warmer. Its delta H is negative, and it means you've formed stronger, more stable bonds. Endothermic, it absorbs heat so things get cooler. Its delta H is positive, and it means the old bonds you broke were actually stronger. Got it? Good.
But look, this isn't just something that happens in a lab or a little plastic pouch. This chemistry is happening everywhere, all around us, all the time. A campfire is probably the most classic exothermic reaction we all know. You're breaking the relatively weak chemical bonds in wood and oxygen and forming super strong, super stable bonds in carbon dioxide and water. That process releases a massive amount of energy as heat and light. And on the flip side, what about ice melting in your drink? Well, for that ice to melt, it has to absorb heat from the liquid around it to break the bonds holding its crystal structure together. That's an endothermic process in action.
What's even crazier is that we figured out how to become puppet masters, pushing and pulling these reactions in whatever direction we want.
We do this using something called Le-Chatelier's principle. And to put it simply, a chemical system is kind of lazy. It likes to be in balance. So if you mess with it, say by adding a bunch of heat, the reaction will shift in the direction that uses up that extra heat. So for an exothermic reaction that's already producing heat, adding more heat actually makes it run backward. But for an endothermic one that needs heat, adding more heat pushes it forward.
And why should you care about this? Well, this one principle is the backbone of modern industry. Take the Haber-Bosch process. It makes ammonia for the fertilizer that grows our food. We're talking one of the most important inventions in human history. It happens to be an exothermic reaction. So, to get the most fertilizer possible, engineers actually run the process at cooler temperatures to keep forcing the reaction forward. It's brilliant.
Now let's bring this all the way home to the most important application of all, you. This constant tug-of-war between exothermic and endothermic reactions is literally what powers all life on this planet.
And it all starts right here. Photosynthesis is the ultimate endothermic process. Plants take in simple, low-energy stuff like carbon dioxide and water, and they use the energy from sunlight to build them into complex, high-energy sugar molecules. They are literally packing sunlight away into chemical bonds. And then we come along. We eat the plants, or we eat animals that ate the plants, and our bodies do the exact opposite reaction, cellular respiration. It's a powerful exothermic process where we break down those energy-packed sugar molecules. That releases the stored solar energy, and we use it to power our muscles, to fire our neurons, and to keep our bodies warm. Every single breath you take is part of this beautiful, balanced cycle.
Which brings us to one last really fascinating question. If the universe tends to favor stability, those downhill exothermic reactions, then why do these uphill endothermic reactions even happen spontaneously? It kind of seems like it breaks the rules we just learned, but it's really a clue that energy is only half of the story. The other half is all about disorder and the universe's unstoppable tendency to get messier, which is a whole other rabbit hole to go down.